How's it going, guys? Today we're going to be going over module 6.2, day 1, graphing polynomial functions. And we're first going to go over investigating the end behaviors of graphs of simple polynomial functions. So a polynomial function of degree n has a standard form, p of x equals a n x to the nth power plus a n minus 1 x to the n minus 1 power, and so on and so forth, to plus a2 x squared plus a1x plus a0, where an minus 1, all the way to a2 and a1 and a0 are all real number coefficients, except for that a of 0. That a of 0 is just a constant. Regardless, they're just real numbers with no variables. So an example, 3x to the 5th minus 2x to the 4th plus x cubed plus 7x squared minus 4x. The 3, the 2, the 1 in front of the x cubed, the 7, and the negative 4 would be what your a values are. Well, the x to the 5th, x to the 4th, x to the 3rd, x squared, and exit, and the x are your x raised to the n minus 1, all the way down to n power. A polynomial function can be classified by its degree. For instance, x to the 4th power is in degree 4, and it's called a quartic function, and x to the 6th is in degree 6, and it's called a 6th degree function. And in the following table, just keep in mind that those graphs are meant to go on forever on each way. We don't have the arrows, but we're just going to assume they're there anyway. So for this table here, we have the function f of x equals x. That's what the graph looks like. The domain will be from negative infinity to positive infinity, and the range will be from negative infinity to positive infinity as well. And the end behavior, we can look at the graph and we can see as x is increasing, the y's are increasing as well. And as the x's decrease, the y's decrease as well. So as x goes to infinity, f of x will go to positive infinity. And as x goes to negative infinity, f of x will go to negative infinity as well. For f of x equals x squared, the domain you can see is negative infinity to positive infinity. We hit every single possible x value. The range, we see this point right here at the bottom. That's our minimum. So we hit every single point from that 0 up to infinity. That's why we have a hard bracket at 0, because 0 is part of the function. So the range will be from 0 all the way to positive infinity. For the end behavior, as x is going to infinity, we can see f of x is also going to infinity. As x is increased, the y's are increasing, and as x decreases, we see the y's are still increasing. So as x goes to infinity, f of x is going to positive infinity as well. As x goes to negative infinity, f of x is going to positive infinity. F of x equals x cubed. That's what the function will look like. The domain, we see we hit every single possible x value. So the domain is from negative infinity to positive infinity. And the range is from negative infinity to positive infinity as well. And for the end behavior, we can see as x increases, the y's increase. And as x decreases, the y's decrease with it. So as x increases, f of x is going to infinity. As x goes to infinity, x goes to negative infinity, f of x is going to negative infinity as well. For f of x equals x to the 4th power, we can see that it looks very, very similar to f of x equals x squared. F of x equals x to the 4th power is just a little steeper. This part right here is a little wider. And they are actually very similar. The domain, range, and the end behaviors of f of x equals x to the 4th and f of x equals x squared are the exact same. And we can see that because both graphs look very similar. The domain is still negative infinity to positive infinity. The range is still 0, including the 0, up to positive infinity. And the domain, we can see as x increases, the function f of x equals x to the 4th is going to positive infinity. As x is going to negative infinity, f of x is going to positive infinity as well. As f of x equals x to the 5th power, that also looks very, very similar to f of x equals x cubed. And same thing, they're very similar. They have the same domain, range, and functions, and behaviors as f of x equals x cubed. It's all real numbers for the domain, all real numbers for the range, and the end behavior is the same thing as f of x equals x cubed. As x is increased to infinity, f of x is also going to infinity. As x is going to negative infinity, f of x is going to negative infinity as well. In the last row, we have f of x equals x to the 6th power. It looks very, very similar to f of x equals x to the 4th, and f of x equals x squared. That's because the exponents are the same, even exponents will look very similar, and odd exponents will look relatively similar as well. And even exponents will have the same domain, range, and behaviors as each other, and same thing with the odd ones. That's why f of x equals x to the 6th power will have the same domain, range, and end behavior as f of x equals x to the 4th and f of x equals x to the 2nd power. The domain will be negative infinity to positive infinity. The range is still 0 to positive infinity. And the end behavior is as x goes to infinity, f of x will go to infinity. As x goes to negative infinity, f of x goes to positive infinity. For the next page, we're going to be looking at the same functions, except we're multiplying it by a -1 now, or in other words, we're flipping it over the x-axis. So f of x equals negative x. The domain and range stay the same as it was before. It's still all real numbers for both. The end behavior is what flips. Now the end behaviors are the opposite of what it was before. We can see that as x is increasing to positive infinity, the y's are actually decreasing downwards to negative infinity. And vice versa, as x is decreasing to negative infinity, the y's are increasing. So as x goes to positive infinity, f of x is going to negative infinity. As x is going to negative infinity, f of x is going to positive infinity. For f of x equals negative x squared, it's just a reflection over the x-axis. So the domain stays the same. It's still going to be all real numbers, but the range is going to change. Since that 0 that was the minimum is now the maximum, we can see that the graph is going from negative infinity to 0 for the range, including that 0. And just like before, the end behaviors are going to flip. There's going to be the opposite of what it was on the previous slide. So f of x equals negative x squared. As x is going to infinity, f of x is now going to negative infinity. As x is going to negative infinity, f of x is going to negative infinity as well. For the third row, we have f of x equals negative x to the 3rd power. The domain and range are still all real numbers. That doesn't change from f of x equals x cubed, but the end behaviors are going to flip. They're now the opposite of what it was on the last slide. So as x is going to infinity, f of x is going to negative infinity now. And as x is going to negative infinity, f of x is going to positive infinity. F of x equals negative x to the 4th. This looks very, very similar still to f of x equals negative x squared. And same thing, the domain, range, and end behavior will be the exact same. So the domain is still all real numbers. The range is now negative infinity up to 0, including that 0. And as x is going to infinity, f of x is going to negative infinity. As x is going to negative infinity, f of x is going to negative infinity as well. For f of x equals negative x to the 5th power, it's very similar to f of x equals negative x to the 3rd power. The domain, range, and end behaviors will be the same. And if you compare this to the previous slide, you compare f of x equals negative x to the 5th with f of x equals x to the 5th. The domain and range stay the same. The only thing that changed are the end behaviors. They flipped. So now it's as x is going to infinity, f of x is going to negative infinity. As x is going to negative infinity, f of x is going to positive infinity. And for the last row, f of x equals negative x to the 6th power. It looks very similar to f of x equals negative x to the 4th and f of x equals negative x squared. And they behave very similarly as well. The domain, range, and end behaviors of all three functions are the exact same. The domain is all real numbers, negative infinity to positive infinity. And the range goes from negative infinity up to 0. And the end behavior, as x is going to infinity, f of x is going to negative infinity. As x is going to negative infinity, f of x is going to negative infinity as well. So let's go on. This slide is basically summing up everything we said in the last two slides. For f of x equals plus or minus x to the nth power, the domain is always all real numbers, or in interval notation, negative infinity to positive infinity. In this next line, there's a little typo in the notes. It should say range depends on whether the degree of the function is. And that range depends on whether the degree of the function is even or odd. Okay? If it's even, then the range of f of x equals x to the nth power, and f of x equals negative x to the nth power. That's going to be 0 to infinity and negative infinity to 0, respectively. If it's odd, then the range of f of x equals x to the nth power and f of x equals negative x to the nth power is going to be all real numbers, or negative infinity to positive infinity. The end behavior of f of x equals negative x to the nth power is always the opposite of f of x equals x to the nth power, regardless if n is even or odd. Okay, so now we're going to be looking at x-intercepts at turning points of polynomial functions. So a polynomial function of degree n has the intercept form p of x equals a, x times x minus 1, x times x minus 2, so on and so forth, to x minus x to the nth power. Or sorry, x to the n. Where a, x to the 1, x to the 2, all the way up to x to n are real numbers, and x1, x2 to x to n are x-intercepts. Also, something else to keep in mind, each one of these terms, so that a, x minus x1, x minus x2, and that x minus xn, all four of those, and everything you're multiplying with each other, all those things are called factors. We're gonna go through the terminology a little bit more later on, but something to keep in mind is that each one is called a factor, and each factor will give you one distinct x-intercept. For instance, this x minus x2, this will give you the x-intercept x2. And this x minus xn will give you the x-intercept of xn. So to put this in real numbers, let's say we have some f of x equals x times x minus 3 times x plus 3, or so x plus 4. The x minus 3, and the x plus 4 are all factors of f of x. Each one will give you one distinct x value. If you have this x by itself out here, that tells you we have an x-intercept. It's like you do this in the bottom. So this x right here will tell you that we have an x-intercept at 0. And this x minus 3 will tell you we have an x-intercept at x equals 3. And this x plus 4 will tell us we have an x-intercept at x equals, sorry, that's supposed to be negative 4. And each one of those are a factor, and each factor gives you one distinct x-intercept. And we're going to touch on this a little more later on, but I think it's a good thing to keep in mind while we go on for the next couple slides. Okay? So going on, a turning point will describe the graph moving away from the x-axis and then back, or vice versa. Or in other words, these are your hills, your valleys, the point where the graph goes from increasing to decreasing, or decreasing to increasing. However you want to think about it, those are what your turning points are. A polynomial function can either cross the x-axis at the x-intercept or be tangent to the x-axis at the x-intercept. And the word tangent is just a fancy way of saying that it bounces off the x-axis and goes back. What I like to think about is I like to think about the x squared graph. So f of x equals x squared. And f of x equals x squared has an x-intercept at x equals 0 at the point 0, 0. And we can see that the graph f of x equals x squared is going to go down until it touches the x-axis, and then it bounces right back up. That point right there where it touches and bounces back up is said to be tangent to the x-axis, or in other words, it's just touching and going right back up. That's what it means to be tangent. A turning point is also considered a maximum or minimum, so they can be kind of used interchangeably. Also, a maximum or minimum is considered global or absolute if the function never takes on a value greater than the maximum or less than a minimum, or in other words, that turning point is the absolute greatest or absolute minimum point on the whole graph. Okay? So for instance, we have this graph over here. We can see where it's circled, this turning point that's circled over here. That's called a global or absolute minimum because it's the absolute smallest point on the whole graph. There's no point less than this point over here. Going on, a maximum or minimum is considered local or relative if the function does not take, does take on a value greater than the maximum or less than the minimum. In this case, we have this turning point circled over here. And what I like to do is I like to look at each turning point, and I like to think, okay, is this a minimum or a maximum? We can see this is decreasing and increasing, so that point is going to be a minimum. So I know it's either going to be a local minimum or a global minimum. So from there, I'll compare to the other turning points, or sorry, the rest of the graph, actually, and see, is there any points on the graph that is lower than that point? In this case, we can see we have all these points underneath this dotted blue line are less than that turning point. So we can say that's not the smallest point on the graph, so it cannot be a global minimum. So in that case, if it's not a global minimum, that means it has to be a local or relative minimum instead. And all global, absolute, local, and relative mins, they all have to be a turning point. Okay? So let's keep going. Now we're going to fill out this graph. A good thing to do is to pause this video in between each function and graph the function on decimals.com or on a graphing calculator, whatever you prefer, and follow along as we kind of go through the characteristics of each function. So the function f of x equals x to the third power. The x-intercepts, we see we have one factor, which is just the x to the third power. So we have one x-intercept, and that's at x equals 0. That's our x-intercept, x equals 0. And there's a cross or is a tangent at the x-axis. And it's going to cross the x-axis at that point. How many turning points do we have? We actually have no turning points. And that's because there's no time in this graph, or sorry, in this function, where the function goes from increasing to decreasing or decreasing to increasing. It slows down how fast it's increasing next to the x-intercept, or sorry, next to the x-axis. But it never actually goes from increasing to decreasing. So in that case, we have no turning points. And since we have no turning points, it's impossible for us to have any global maximums, local maximums, global minimums, or local minimums, since all four of those have to be turning points themselves. If we don't have any turning points, we can't have any of those. And our graph is going to look something like this. And we can see in this part over here that indeed we do kind of start increasing slower, but we don't actually go from increasing to decreasing, and that's why we have no turning points on this graph or on this function. All right, so now we're going to go to f of x equals x squared times x minus 2. If you can, pull up the graph, see what it will look like, so you can follow along with me. The x-intercept of this function, or the x-intercepts, are x equals 0 and x equals 2. And we can see we have two distinct x-intercepts because we have two different factors. So we have two different x-intercepts. And now we have 0, so x squared equals 0 when x is 0, and x minus 2, that 2 is going to give us our x-intercept for that factor. There's a cross or is a tangent. When x is equal to 0, it's tangent. And when x is equal to 2, sorry, when x is equal to 0, it's tangent. When x is equal to 2, it crosses. How many turning points do we have? I'm not sure why I did that, but we have 2 turning points. Do we have any global maximums? We have no global maximums. We don't have, we have one local maximum. We have no global minimums, and we have one local minimum. If you compare to your graph, or sorry, on the graph that you have, that you should have up on decimals or on your graphing calculator, we can see we have a relative or local maximum and a relative or local minimum. And our function is going to look something like this. We have an x-intercept at 2. We go up. We touch at x equals 0, so we're tangent at it. We go back down. Then we go back up through x equals 2. And we can see where x equals 0, that point right there is a local or relative maximum because it's a turning point, and we see we're going from increasing to decreasing. It's a hill, so it's going to be a maximum. But at the same time, if we draw a line right here, All these points right here going on forever are all bigger than that turning point. So we don't have a global maximum at that point. We only have a local maximum. And the same thing at this point over here. I'm not sure what point it is, but that's a turning point right there. And we see it's a valley. Since it's a valley, or it's going from decreasing to increasing, it's going to be some type of minimum. And since we have points less than that turning point, we can see all these points down here. Since it's going down forever, we're going to have an infinite amount of points smaller than that turning point itself. So we can say that it can't be a global minimum since we have an infinite amount of points less than that turning point. We have a lot of points less than that turning point. So if it's not a global minimum, it has to be a local minimum. And for the last function over here, we have f of x equals x times x minus 2 times x plus 2. We see we have 3 factors now, so we're going to have 3 different x-intercepts. And we can see that it's going to be x equals 0, x equals 2, and x equals negative 2. And we get that from our factors over here. And do they cross? Are they tangent at the x-axis? All 3 of them just cross through the x-axis. You can see that on the graph you have up. How many turning points do we have? We also have 2. We don't have any global maximums. We have 1 local maximum. We have no global minimums. And we have 1 local minimum. So let's go ahead and graph it, see what it looks like. We have an x-intercept at negative 2, at 0 and 2. So we're going to go up through negative 2, through 0, and through 2 again. Or sorry, through 2. And that's what our graph will look like. We see we have 2 turning points over here. And if we look at each one individually, let's look at the one between negative 2 and 0, top one. We see that's a hill. It's increasing to decreasing. So we know it's going to be some type of maximum. So now we need to decide, is it a global maximum or a local maximum? We can see that the graph is going upwards forever, so it cannot be a global maximum. So if it's not a global maximum, we know this point will be a local maximum. And if we look at the second one, the valley on the right side between 0 and positive 2, that's a turning point. We can tell it's a minimum. Since it's in a valley, it's going from decreasing to increasing. Now we need to decide, is it a global minimum or a local minimum? And we can see on the left side over here that this graph is going downwards forever. And since it's going down forever, we can't have any type of minimum on this graph. So that leaves that turning point to be just a local minimum. All right, for this table over here, what I want you guys to do is actually pause the video for a second and then actually try doing it yourselves. Graph each function through your graphing calculator or with Desmos, and I'll have the answers popped up in a second, and you can compare what you have with what I have. Okay, so this is what you should have gotten. I'm not going to go through every single one, every single function by itself, but what I do want to touch on is on the third column, f of x equals x squared times x minus 2 times x plus 2, where it says global minimums. We have 1 global minimum that occurs twice. In other words, I guess you can kind of say we have 2 global minimums. They have the same y value, so they're both the absolute minimum or the absolute smallest points on the graph, but they're 2 different points. So we have 1 global minimum that happens twice. Okay? So go ahead, look at it, compare yourselves, compare what you got with what I got. Look at the graphs again if you have to. These are rough sketches of what the graphs should look like. It's not going to be perfect, but it's close enough. The important thing is to make sure you have the end behaviors right and that it crosses the x-axis or is tangent to the x-axis where it needs to be. And so you have a rough sketch of it that's pretty much good enough. So let's go on. Let's do one more slide for this video. And last thing I want to touch on is what we talked about earlier, that each factor is going to produce 1 x-intercept. If the factor is raised to an odd power or exponent, then the graph will cross the x-axis. If the factor is raised to an even power, the graph will be tangent to the x-axis. For instance, let's think about f of x equals x cubed. Let's actually move this quiz warning down here. So f of x equals x cubed. That's an odd power, it's an odd exponent. And that's why when it crosses the x-axis at x equals 0, it just crosses it normally. It doesn't bounce, it's not tangent to it, it just crosses. But when f of x equals, let's say, x squared, something we're familiar with, we know the x-intercept on that graph is at 0, 0. And that's when we go down and we touch at 0, 0, we bounce right off of it. It's supposed to be more curved, not an actual point like that. It bounces off of it, and it's considered tangent to the x-axis. Since it just touches it and bounces right back off, that's what's known to be tangent to the x-axis. So that's what determines whether something is crosses it or if it's tangent. We can know that by the power of that specific factor. So let's actually go back really quick, look at a previous slide. Let me pop these up really quickly. And I actually want to look at f of x equals x squared times x minus 2 times x plus 2. We have three factors here, x squared, x minus 2, and x plus 2. The x squared factor is even. That's what's giving us our 0, since x squared equals 0 when x is 0. So the factor, the x-intercept, x equals 0, comes from that factor. And that's why on the graph here, we bounce over tangent to the x-axis at that factor, since the power of that factor is even. But on the flip side, if x minus 2 is raised to the first power, if 1 is an odd number, since 1 is an odd number, that's why the x-intercepts x equals -2 and x equals 2, they both just cross the x-axis, since 1 is an odd number and they're both raised to the first power. So 1's odd, and at those x-intercepts, we're just going to cross the x-axis since it's raised to an odd power. Okay? And the rest of the notes for day 2 we'll go over in the next video.